Let's concentrate on polar. So the idea of the polar was in the cylindrical coordinates, which we're going to do today on the quiz. There's a cylinder built, and that's when we use cylindrical coordinates. For cylindrical coordinates, we're imagining, this is polar, but you're imagining a cylinder, let's do below and above, and the point on the cylinder, on the shell of this soup can. How to describe this point? We agreed to describe this point as height will be z. That's what today quiz. Height is z, and then you go into 2D, shrink the can into flat, and then on the floor we're doing typical 2D polar coordinates, which is theta and radius r. R was in 2D. Then the polar coordinates show up, and they said, no, that's actually not convenient to have z involved at all. Let's completely get rid of x, y, and z forever and describe this point using angles in 3D. And that's how the two angles show up. Theta is still rotating in 2D. Rho now is the radius in 3D. So rho is how far I am from the center in 3D. And phi is the angle with the z-axis. There was lots of questions how phi goes from here to here or from here to here, and I was reading about it, and actually it's the second way. So phi is checking how am I bending up and down, while theta is rotation. Theta is doing the whole rotation from 0 to 2 pi, while phi was only restricted from flat to flat, so from 0 to pi. I was reading about why, and I was actually right about it. They said that to have bijection, you don't know what bijection is, but the idea is you should not overdo, two angles should not overdo each other. So since this one already performs the full rotation, the other one should not perform the full rotation anymore, because it's going to be too much. That's kind of the easy way to explain what bijection is. Basically, remember we taught you one-to-one functions, one input, one output. There should be no extra overlapping. So if angle is here, if your point is here, this phi, for example, is pi over 4. If point is here, you have to recalculate this angle again. What is that? Pi over 4, I would say 2 pi minus pi over 4, something like that. Yes?
Oh, I was just going to ask, could you think of theta and rho as being, I'm sorry, not rho, phi as being interchangeable? So you did, what is it, 0 to pi on phi, then you would do 0 to 2 pi on theta, but could you do the reverse?
I actually saw, it's a good question, not in America. I saw that European books do switch them. But here they agreed to use theta to be in 2D and phi to be up and down. But I saw the books that do the opposite. For example, this one. This is the book I copied randomly. Did not notice it was actually European book. You see what they're doing here? Phi is on the bottom and theta is at the top. So he actually guessed right now. And that's why I decided to fix it for you. So yeah, it's just, after all, how you call functions. And that is not something people agreed on. They just agreed to use these letters, that's all. So that is the idea, and that's why this idea of the cone, upper cone, was created with the only one formula. Phi is fixed as pi over 6. This is pi over 6 with this point and 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 this point. Is the angle with z-axis is pi over 6. While if you want to have the lower part of the cone, it will be 5 pi over 6. So it's here, here, all these points. What kind of angle they're creating with z-axis. So that's the idea. So it's going to be the hardest part for you to imagine the z-axis idea. And then the formulas will be the hardest part to memorize. I remember that x is r cosine theta, but now r is rho. Rho is 3D r. Y is r sine theta, and each multiplied by sine phi. And then z is multiplied not by sine phi, by cosine phi times radius rho. Anyway, many ways to memorize it. Try to do it the way you can. And we almost finished this example we had. And the formula, now instead of r d theta, you will have r, which is rho, times r sine theta. And that's why this r squared shows up. R squared sine theta is now part of the formula, which is also something you'll have to memorize. So 3 things to memorize here. Complicated formulas, this new formula, and what phi means. That's why it's the last chapter of the all triple integrals. It is the hardest one. So we were trying to finish this example. We were almost done. We were trying to build triple integral of some kind of function z, where e bounded by those 2. And we were like, oh, what are those 2? Z squared equals x squared plus y squared, which is coming from formula number 1. That is a cone. From formula number 2, z squared equals 4 minus x squared minus y squared is a sphere. So again, it's like very typical example. We will keep working on it all the time. It's a half of the sphere, cut it with the cone inside, and we're looking at the e between. So I told you the answer. Now finally let's figure out why is the answer like that. There was some kind of easy part and hard part. So I would say angles here are more or less straightforward. So maybe let's do angles first. So skip some space, we're gonna finish this. Angles from the picture are more straightforward, so I kind of see that first. No, actually, not really. Let's do in order. I don't know what is gonna be easier for you, so let's just do in order. Z equals from this first equation, number 1. This was given, equation number 1. From the first equation, number 1, z equals square root of x squared plus y squared. But we can change it into square root of r squared, because as always, this is r squared. So this is r. So it's very interesting. Z matches with the radius r all the time. Whenever I'm going away in 2D, r is in 2D. This will match with z height. What kind of triangle is that? Let's see. R is in 2D, remember that, not in 3D. So this is my R. If I am here, z will be the same here. If I am over here, z will be the same here. What kind of right triangle with 2 the same sides is gonna give you the angle right in between them? So
a right isosceles triangle.
Right? And the whole idea is what this gives it. What angle it gives you having the same sides.
45 degrees.
45 degrees, so that's kind of it's coming from here. Also, you can see that you can write down as rho, this is rho, cosine from the triangles. Phi equals rho sine phi. The sides are the same. Let's divide by rho. Since it's radius, it's not 0. When does cosine phi equals sine phi? When tangent is 1. Or basically you can figure out just one angle when they equal. On the restricted domain, phi is pi over 4, just like you said. That is coming from this triangle that r in 2D matches with z height. And then this line cuts it through to create the cone. Well, what kind of angle is that? Pi over 4. So that makes sense, because these are the same, and so on. So at least we know phi now. Phi, we were looking for this angle. This is what we needed, this angle. This is phi. Now we know that phi is from 0 to pi over 4. Cone in general will cut some kind of angle, so it's not going to be any more from 0 to pi. But what kind of angle is cutting? That depends on the formula. Other 2 things, that's what I wanted to say, are actually pretty straightforward. Also, let's see, let's figure out other 2, radius rho and theta. Theta is rotation on the floor. Is it full rotation for the cone?
Yes.
Do you all see? The cone is completed. Since it's full rotation, theta is from 0 to 2 pi. Now the radius. The radius in 3D. How far does it go? You might think it's going over here. No, it actually stops at this intersection. So we need to know how far this intersection goes. I don't have so few colors. Here, this is my row over here. The intersection comes from, when do they meet? Well, they meet at the sphere, right? What radius sphere has? 2 squared. So since the radius of the hemisphere is 2, then we know it cannot go higher than 2. So it's from 0 to 2. From 0 to 2. Then the integral becomes, let me stop here though. How do you feel about that? As you can see, the 0 pi over 4 is the hardest one, to be honest. Everything else still takes you to the polar in 2D, so that's not too bad. Yes?
The 2 pi is, I'm trying to understand, is because the hemisphere goes completely around, and so it has to be on every part of the 2D plane.
We're not talking about hemisphere though, we're talking about this cone inside of the hemisphere. It's like ice cream cone, and that one, you're right, is going.
That the hemisphere kind of encompasses it's not like a semi-hemisphere or like half of the hemisphere. It only covers one side.
Yeah, like so.
Positive x or negative x. It covers that whole basically 2D plane.
Yeah, like that.
And that's why it's 2 pi.
Exactly.
Okay.
You always see the shadow on the floor for theta. So the shadow on the floor will be this smaller circle, right? The shadow, the projection, if you want to be exact. Since the projection have the whole circle, that will be from 0 to 2 pi for theta. Radius is in 3D, so it goes up to 2. And then phi is how much this cut was happened with respect to the z-axis. Pi over 4. Pi over 4. Yes?
So that 2 over there you're talking about, are you talking about the row?
Rho, yeah.
Okay.
Let me write down. Radius rho is 2. It is a radius for the hemisphere, which is coming from this equation number 2. Write it down if you need to. This is where the radius is coming from. Equation number 2. So rho is 2. Not 2 squared though. Yeah. Now we start building the integral. You think this is the hardest part? We did not even start integrating yet. But before we start integrating, which is step 3, step 1, sketch the graph. Step 2, find all the borders, or using any method you understand. Step 3, complete writing the integral. Integral over e, there was a function z inside doing its own thing. dx, dy, dz, any order because we don't know the real order yet, equals integral, integral, integral. So the last integral should be numbers, but in this case all of them are numbers, so we are lucky. But the important thing is to complete the formula first before you put z in. So remember the formula. Rho, so rho squared, sine, phi or theta. There's only 2 angles here, so remember it goes phi. And since theta was never mentioned, theta goes actually usually to the very end, but in this case it didn't put it at the end. Doesn't matter, here you can switch the order. So I usually put theta at the end. I see it like this. Theta was not mentioned because it's the last one, that kind of discriminated all the time. Then the other angle, 2 angles always go together. Radius usually goes first. So this is part of the formula. Rho squared sine phi, theta at the end, next angle, radius. Now what should I do with z? I should not write down z. The whole idea of the spherical coordinates is to get rid of x, y, z.
Oh, isn't it z like rho cosine or something?
Rho, cosine or sine?
Sine.
You actually was right. I wanted you to hesitate and you should be firm. It is rho cosine phi, yes.
Is there a way we can like make the phi and the rho look different? So they always look the same.
They don't look the same at all. No.
I keep writing them down and then I'm looking back at my notes.
Well, see, no, it's pretty easy.
Not in this case. In this case, doesn't matter. One is a spiral. And the other one is literally O with a wiggly part inside. How? Oh, the row. The other one is like. Then make a circle and then like so. No.
That's literally what it says on the thing too. That's how phi
That's a
generally
printed
looks like.
one.
Yeah, but that's how I always wrote it, and that's how my math teachers.
That's a printed one.
No, I use that for zero.
Asya says so you should do like this, but it's a printed one. We actually do use it for other things.
Huh?
We use this one for other things. It's reserved, to be honest.
Well, if it's reserved for other things, you don't really use it in the scope of this class.
Yeah, good point. This one, if you see this one in the printing form, it's actually capital Phi. It's kind of reserved for stuff, so that's why I don't use it. These two, you guys are so picky. You don't know about this. I told you. We have this one, and this one. Psi, and Thay. So you upper level classes will blow your mind. You know, you should not be so picky, okay? That's because you don't learn cursive in schools, right?
I learned cursive.
Oh, if you also look at Greek life,
If you learn cursive, you don't have problems with that.
if you look at the Greek village, they also write phi like that.
Oh, yeah, I definitely know
I'm not
that
sure what else is that reserved for, like phi.
for capital stuff, lots of matrices and
The
stuff, and some
gold
functions. No, some functions reserved. Yeah, I'll tell you later. Yeah, I will tell you later. Okay, let's concentrate. And let's finish. So radius goes first in my case. Radius from what to what? Radius row from what to what? 0 to 2. Phi, which is looking completely different. From what to what? 2.
Wait, no.
Pi over 4. That's the weird one. And finally, which color should I choose here? Theta from 2 pi. That's the one that's usually typical. And now you finish creating the integral. Now you have to integrate that. In this case, it looks very messy for you probably, but your eyes will get used to it slowly. Since all limits of integrations are numbers, you can break it into 3 integrals. Unless some functions are dependent. No, this one's actually good. 1 integral, and 1 integral. Any order, that because limits of integrations are numbers, no functions are involved yet. The outside is from 0 to 2 pi. Do you see any theta function?
Nope.
No, so it's going to be 2 d theta, which is just 2 pi for you to know, right? Did you get used to it? This is just 2 pi, the length of the interval. Next one is 0 pi over 4. That is the one phi. Phi has functions. Which kind of functions? Cosine and sine.
Oh, yeah.
D phi. Interesting. And then the one from 0 and 2, that is rho. Do you see rho?
Yeah.
What kind of?
There's like 3 of them.
3 rho cubed. Do you see it? D rho. And now integrate each carefully. The first one is 2 pi. The last one is also easy. Rho 4 over 4, which is 2 to the 4 over 4. That's the last one. And then the middle one. How would you deal with cosine times sine? Who remembers? There's 2 ways to do it actually.
Sure. Identity.
Is that it? Yeah, I was gonna say.
Number 1, identity. If you remember the identity, of course. If you don't remember, one function is a derivative of another one. What should we use? You can do u substitution. For example, you can choose any of them to be u. The other one is plus minus du. So, if u is sine phi, du is cosine phi d phi, which is exactly standing over here. This is the beginning of the calculus 2 class, usually. Then some of you change intervals, some of you don't change intervals. Both are fine, just know how you do it. It's going to be integral of u du. And then you can change it or not, you decide. If you don't change it, don't forget to write down phi is still 0, phi is pi over 4. That is not, it's kind of an illegal way to do it. but it's working, so it's fine. If you don't change limits of integration, then when you go back, which is u squared over 2, you have to go back to the function with phi. Sine squared phi over 2 plus 0 and pi over 4. 2 pi. 2 and 4 cancels out. What is 2 to the 4 over 2?
32 divided by 2.
16 pi outside. And finally, the answer will be 16 pi. Sine of pi over 4 is...
Square root of 2 over 32.
Right, squared. Squared over 2 squared over 2 again. And all of this is simplified into
Something.
Math.
math, right? This is the hardest one.
A number.
Is it 16 pi?
16 pi, and then it simplifies more. I have 2 pi over here. What do you have?
I got 4 pi.
Let's see, square root gives you 2 over 4 times 2, that's 8. 16 pi.
32 makes it be 4 pi.
Yeah, isn't it 4 pi?
Maybe. Or we lost something. 2 pi, let me see. 2 to the cube.
Because it's 16 times 2 over 8, not 1 over 8.
So that would be
Yeah.
16 pi over 4.
Yeah.
Which should be 4 pi.
Okay, let's keep 4 pi then.
Yeah.
Nice.
The book is wrong.
Good job. Yeah.
We are right.
So keep practicing. This comes to be an easy example. As you can see, there's no function involved yet.
I like it that
And that is the upsetting part of this. So spherical coordinates are used when you're working with spheres or anything looks like spheres, like cones. Let's write down actually. Note. Use spherical coordinates, a joke, when we tell you to do that on the exam, so you do that. Use spherical coordinates when working with spheres. Spheres, such a hard word. Spheres and cones. If you work with cylinders or anything that involves a right line, that will be nice to use z then, because z describes this right line better. Then it's cylindrical coordinates. But if it's something spherical with angles, rotations, then spherical coordinates are better. And spherical coordinates, surprisingly, is the most popular one because it describes lots of things. So this will be, of course, it's not a surprise, it will be the hardest homework from the whole chapter of triple integrals. It's the last homework. So I kind of like the idea of extending the deadline for that one. But you should not get discouraged. Post problems in the forum, we're going to figure it out together. And torture Asya in the office hours. She likes that a lot. She's keep waiting for you and she's crying when you don't show up.
Jacob always shows up.
Maybe that's what she's crying.